A sequence is just a list of numbers. Now take a look at this list of numbers. 2, 4, 8, 16, 32, 64, and it goes on and on. If you notice this, we get the next term by keep multiplying by the same number. In this case, that is 2. So if you multiply 2 with 2, we get 4. If you multiply 4 with 2, we get 8. If we multiply 8 with 2, we get 16, and on and on. So we are getting the next number in the sequence by multiplying by the same number. Let's take a look at another one. Suppose we have 3, 6, 12, 24, 48, and on and on. Here also we are multiplying by the same number. 3 multiplied by 2 is 6, 6 multiplied by 2 is 12, 12 multiplied by 2 is 24, 24 multiplied by 2 is 48. If you wanted to find the next number in the list of numbers or the sequence, you would have to multiply by 2 again. Let's see another one over here. We can have 1000, then we can have 100, we can have 10, we can have 1, we can have 1 by 10, we can have 1 by 100, and on and on. Here what we are doing, we are multiplying by the same number, but this time the multiplication is a fraction. In other words, you can call it a division. It's multiplied by 1 by 10, again multiplied by 1 by 10, multiplied by 1 by 10. So this time we are multiplying by a fraction. So when we have a list of numbers, or when we have a sequence which is built term by term by multiplying by one special number over and over again, we call that a geometric sequence. Geometric sequence, or the logic by which we progress, we can call it a geometric progression, or GP for short. If the terms of a sequence is added together, we call that a series. For example, if we write 2 plus 4 plus 8 plus 16 plus 32 plus, that means if we add up all the terms of this list of numbers of this sequence, we'll get a series. So then we will call it, this geometric progression, a geometric series. So if every number is called a term and we write it as first term is u1, second term is u2, third term is u3, fourth term is u4, and on, then we can say that we can notice what it looks like algebraically. The first term, if we use the symbol a and the number by which we keep multiplying, if we call that number the common ratio, or r, then the second term would be a multiplied by that common number known as the common ratio, so that would be ar. Then the third term would be again multiplied by r, that would be ar squared, and the fourth term, when we multiply that with r, that would be ar cubed. And if you notice it, whatever the term is, it is 1 less, the exponent is 1 less. For u4, ar to the power 3. For u3, ar to the power 2. So we can have a general rule for the nth term, a particular term, and the nth term would be un is ar to the power n minus 1. That means if we have something like this, u1, it would be only a, because 1 means 1 minus 1, r to the power 0 is 1. If we have u2, that would be ar. If we have u3, that would be ar squared. If we have u4, that would be ar to the power 3. If we have u5, it would be ar to the power 4. If we have u6, that would be ar to the power 5. That means when we want to find a particular term, it would be the first term a multiplied by the common ratio. Common ratio is the number by which we keep multiplying, to the power 1 less than the term we want to find. Now let's pick a series from here. So suppose you have this series and we want to find what would be the 10th term. So u10 would be first term a, common ratio r, to the power 9. So let's check. So a is 3. The first term is 3 multiplied by the common ratio is 2 to the power 9. So 3 into 2 to the power 9 is 512, and that turns out to 1536. We can find the common ratio by dividing. The common ratio R can be found by dividing the next term with the previous term, or it could be u3 divided by u2. If you notice here, 4 divided by 2 is 2, or the next term 8 divided by 4 is also 2, or 16 divided by 8 is also 2, or 6 divided by 3 we get the common ratio, 12 divided by 6 we get the common ratio, or 100 divided by 1000 we get the common ratio here, 1 by 10. Take a look at these two list of numbers. One is progressing geometrically, meaning by multiplying by the same number over and over again. This time the common ratio is 10, and the other one by adding by the same number over and over again. Suppose if this starts from 0, this would be 10. Now take a look here. By the sixth term, the geometric progression, which has a common ratio of 10, has become 1 million. That's a lot. That's a million. But in case of an arithmetic progression by which it is increasing by 10, the common difference is 10. Even if it starts from 0, doesn't matter. By the sixth term, it can only be 60. That means the geometric progression increases very, very rapidly. So you can say that it is diverging. Diverging. Now, it doesn't really matter whether the value of the common ratio is positive or negative. Either way, if it was negative, then it would be decreasing, and it would be decreasing very, very rapidly. But either way, the values would be very, very large. So when we have a geometric series where the common ratio is either positive, more than 1, or negative, less than 1, regardless of whether the value of R is plus 2 or minus 2, plus 3 or minus 3, plus 4 or minus 4, the point is, if the absolute value, regardless of the plus minus sign, is more than 1, then the geometric progression is going to have terms with very, very large value, and we call this geometric progression diverging, and it has a special sum of n terms. So the sum of n terms would be Sn equals to first term multiplied by the common ratio to the power n minus 1 divided by common ratio minus 1. This will only work for diverging geometric progression. In case of arithmetic progression, there is no such thing as diverging because it is increasing very slowly. So when we are talking about a GP, it is very, very important what the common ratio is. Based on that, we can find the value of the sum of n terms. Take a look at this GP series, which is decreasing very rapidly. If you want to find the common ratio, you can find it by dividing the next term with the previous term. So 10 divided by 100 is 1 by 10. So now we are multiplying by 1 by 10, 1 by 10, 1 by 10. It very rapidly becomes a very small number. 1 by 1000 is 0.001. Now if you take a look at the arithmetic progression, which is here decreasing by 10, so this is minus 10, this is minus 10, this is minus 10. Even after the sixth term, it is not much. From 100 it became 50, but here from 100 it became 0.001. So there is a major difference between the way this GP series, this GP sequence is decreasing and how the arithmetic progression is decreasing. So here it is decreasing very rapidly. To such an extent, after a point, it would be so small that we don't have to consider the terms any longer. We call this type of geometric progression convergent or converging. Here what happens, the value of the common ratio is between negative and positive. It means it doesn't matter whether it is positive or negative. All that matters that it is a fraction less than 1. Regardless whether it is plus or minus, it is a fraction less than 1, and that would make the geometric progression converging, and in case of converging geometric series, the sum of n terms is going to be Sn equals to first term multiplied by 1 minus the common ratio to the power n divided by 1 minus the common ratio. So there's a major difference between a diverging geometric progression and a converging geometric progression. There is no such thing in arithmetic progressions. Now here is an interesting thing going on. After a particular term, the value of the term becomes so small, it doesn't matter what the next terms are. For example, if we have a term 0.00000001, it doesn't matter. We can ignore it. We can say that the geometric sequence or the geometric series stopped over here. So here we can find the sum of all the terms, known as the sum to infinity. Sum to infinity means sum of all the terms, and it is given by a symbol which is a lazy 8. This is the symbol for infinity, and the sum to infinity is the first term divided by 1 minus common ratio, and the sum to infinity will only work if it is a converging geometric progression, otherwise it is not going to work. A quick recap: a sequence is a list of numbers. A series is the sum of the numbers in a sequence. A geometric progression is progressing by the common ratio rule. That means you keep multiplying by the same number and you get the next term, and that term is known as the common ratio. The common ratio. How do you get the common ratio? The common ratio is the next term divided by the previous term. The next term divided by the previous term. That's the common ratio rule. If you want to find the nth term, a particular term of a geometric progression, un is going to be first term multiplied by the common ratio, which has a power 1 less than the number of terms you're wanting to find. Now for the sum of the first n terms, there are two categories. One is the diverging Gp, where the value of the r can be more than 1 or the value of the r can be less than -1. Here the sum of n terms is Sn, first term multiplied by r to the power n minus 1 divided by r minus 1. In case of converging geometric progression, where r is between -1 and 1, here we have sum of n terms is a multiplied by 1 minus r to the power n divided by 1 minus r, and here we have a special situation for converging geometric progression. We have sum of all the terms known as sum to infinity, which is a by 1 minus r. You have to be careful. This is the symbol for alpha, this is the symbol for proportionality, and this is the symbol for infinity, a lazy 8.